Hello, in this video we will see the concept of virtual ground. So let's see from the figures. Okay, so first is this. If you see here, this is 2 volt. Okay, so if you see this figure, we have 2 volt here and 1 volt here. Okay, so by the superposition theorem you will get something this one. So this voltage is this. Okay, 1 plus 1.5. Now if we interchange this potential, this and this, 1 and 2, if the resistance are same, this and this, then we will get the same voltage here. Okay, now if both the voltages are same, then this voltage will be same, 2 volt. Okay, so till now nothing important, just the superposition theorem. Okay, applied. So again we will go and we'll see here, if this voltage is 2 volt and this voltage is minus 1 volt, again we will apply the superposition theorem and we will get some voltage half. Okay, now if we interchange this voltage here, 1 volt and minus 2 volt. Okay, so earlier this was plus 2 and this was minus 1, now it is plus 1 and this is minus 2. Okay, so the concept is the voltages are not same and also in opposite direction. Again we will see by the superposition theorem that this was half, this is minus half. So the point is, till now the point is, whenever you will see any voltage across this type of structure, R, VA, VB, so this voltage will be decided by the superposition theorem. Okay, now if you see this voltage from first figure, 2 1 1 2 2 2, and if they are in opposite voltage, positive and negative, plus 2 minus 1 plus 1 minus 2, in those cases we have some voltages plus or minus. Now if you see here closely, the real concept starts now. If you see here closely, this is plus 2. I'll make this a level for you. Okay, so let's say this is plus 2 and this is minus 2. Okay, so total current here is 0. Okay, and the voltage at this point is also 0. If you apply superposition theorem, it will, the voltage is 0. If you apply the KVL, if you apply the superposition theorem, the voltage is 0 here, and if you apply the KVL, the I comes to be 0, or KCL, I comes to be 0. So the point is, when the equal and opposite voltage is applied across this type of structure, when R, this is plus V, this is minus V, then the voltage here is, if this is R, this is R, is 0 volt. Okay, and the current here is I is equal to 0. So this is the first concept. Now let's go, and if we add one more from this figure, from here, if you see, if you add one current source here and here, and the magnitude is same, just the direction is opposite, and the potential is kept same here, both plus 2 and here minus 2. See the difference. From here to here I have added one current, from here to here I have added one current source in both the side in opposite direction. So one current, 1 ampere is coming here and it is going there, this side, and the +2 because the resistance has +2, and -2 because here the resistance has potential -2. Now if you see closely, the green color, this one, so the current will be same, so this is the path of the current, okay, the green one. Now the red one, I is equal to 0, okay. So what is the V here, what is the potential here? So if you apply the KCL, simply you will get 0 volt, okay. Now we can see this figure in this way also, that there is a current source, there is a resistance, and this voltage is same for this current source and resistance, that is Vx, okay. Similarly here is the current source, but the direction of the current is in this direction, it was here, and in this that it is this direction, in this in the right side. So the magnitude of the current is same, but direction is opposite, in this way and this way, and the resistance is same. Only thing is that this is Vx and this is minus Vx. Then if you see, this potential will be the 0 volt. How? Because if you apply the KCL here, if you see here, if you apply the KCL, you will get the 0 volt, because both this current is same, that will be cancelled, and the current through this resistance, if you see here, the resistance 2 minus V upon R, and here minus 2 V, so V minus 2 upon R. So if you apply the KCL, you solve this, your voltage will be 0. Or you can say that the current through this resistance, through these R0 is 0, okay. So basic concept of this virtual ground is, if you see here, so the basic concept of virtual ground is, first this Vx, these two voltages has to be equal and opposite, okay. And second thing is, same current should flow here and here, this direction, then this potential will be 0 volt, okay. Now if you see another case, let's say here, if you see here, this is +2, this is -1, okay. So you have some potential here, half voltage. Going further, if I add one current source in this direction and here in this direction, keeping the voltage same here and here, you can see that even though this current is same, but this IR current in this loop current is not equal to 0, and because of this there is some potential here, half. So if you make this visual, if you make the visualization like this, so this is the current source and this is the current source, this is the resistance, this is the resistance, okay, and this is the potential which is not equal to this, V1 is not equal to V2, then you will see there is some potential here at this node, because IR, the current through resistance, is not equal to 0. So if you see difficulty in visualizing this figure, you can assume something like this, okay. So you will be able to see the current direction, current flow easily, and because of that you will see that there is a potential here, okay. One more concept, if the potential is 0 in both the point, then obviously there will be no current and this potential will be 0. So this can be also say that there is a current source, let's say 1 ampere current source is there. So in this structure, in this figure also, if you see that there is no current here and this potential is 0, okay. You can visualize this in this way also, that you have this potential 0 and this potential 0, okay, and there is some current source here and there is some current source here, equal and opposite direction. Then because this is 0 volt and this is 0 volt, there will be no current here. IR is equal to 0. Current through these resistance, if you see here closely, this resistance is 0, and because of that your node voltage Vp or Vs, source voltage, is 0. So this is the basic concept of the virtual ground. So if you want, I can summarize this thing in a simpler way. The concept of virtual ground is simple, that if you have, let's say, R and R, this is +2 just for the example, and this will be V. What is the V? So if you see the current is equal to 0. So what does it mean? So this will be what? This will be 0 volt. How come? So if you apply the superposition theorem, it will be 0 volt. Or you can say, let's see how, that this will be 2 upon 2R, the current, from the superposition, 2 upon 2R multiplied by R, that is the first, and second is minus 2 upon 2R into R. So total is 0 volt. Okay. Now if I see here, if I add one current source, same potential, +2, -2, and this -2, +2, -2, and in the opposite direction, let's say 1 ampere, -2, then this current will be same. And if we apply KCL here, so 2 minus V upon R, this will be equal to this current, V minus -2 upon R. So 2 minus V, V plus 2. So minus V is equal to V, or 2V equal to 0, V equal to 0. So this potential will become 0 volt. And I can make this figure as this also, that I can make this as a current source, and since this is +2, so let's say Vx some voltage, and both resistance and current source has the same potential R, and let's say this is gmVGS, same current will flow, and here also R, same potential, current direction is opposite but the magnitude is same, and the magnitude is gmVGS. So this potential is Vx, this potential is minus Vx. So here if you see +2, -2, same current, so here also same current, then this potential will be 0. Why? Because current through this R is equal to 0. Okay, so this is the basic concept of the virtual ground. Thank you.